Okay, good afternoon, everyone. I am Simone Grimaldi, PhD student at the Department of Information System and Technology at Mid-Sweden University. My research topic is reliable wireless communication in the industrial context. We can start with understanding what Industrial IoT is. Well, Merzad gave a pretty interesting presentation of it. Industrial IoT has many advantages arising from the capability of sensing all around the industrial environment. For example, we have the help of big data analytics and providing hypothetical 24/7 predictive maintenance, or the advantages of processing this data with AI, machine learning systems, advanced algorithms, as well as using wireless system for industrial automation. So this is slowly happening. Today we will have a quick overview of what are the challenges of the communication, of the wireless communication itself in the industrial context. Of course, there is a pivotal role of wireless communication technology, which are widespread and now mature since they are out since 15 years. These wireless technologies, they use the unlicensed bands, which are free, so you can transmit on these bands without paying anything. You can develop your own transmission systems. But there are challenges. First of all, the communication requirements specifically for the automation domain are quite challenging and are quite wide, quite broad. The wireless medium is unpredictable per se. Since there is wireless interference, anyone can transmit, and you cannot really control this, and radio propagation issues are quite challenging to solve. Also, IoT is made of small devices, possibly low cost. We don't want to spend thousands of euros or dollars on a single device, since we have to buy hundreds, maybe thousands, I don't know. These are great challenges in the context of industrial IoT. In particular, the second challenge in the radio context is wireless coexistence. Why do we care? Well, there is massive diffusion of wireless technology, in particular at 2.4 gigahertz, because it is an unlicensed band. We have Bluetooth, low energy, Wi-Fi, and all the technologies in industrial scenarios arising from ZigBee protocol. And these are widespread. In this room, there will be tens of these devices working in this exact moment. Anyway, all these standards have low intelligence for opportunistic medium access. They do not cooperate with each other. Sometimes they do not cooperate with within a single network. For a fair transmissions, fair spectrum usage. The effect is that if these systems are coexisting, there is a significant reduction of communication performance of the system that you're willing to deploy, and the quality of service of your application will decrease, will be unpredictable at best. Opportunistic medium access. So how do we solve this problem? Okay. I want to show you something. This is what we would like to see on a radio channel. This is time domain, and we would like to see a free channel. No one is transmitting, and you can deploy your wireless network, and your wireless network can adopt some mechanisms for transmitting, for allocating the time resource. In reality, what you will find in a normal Wi-Fi interference is you put a network spectrum analyzer here, and you plot what you see in the time domain. You will see something like this, which doesn't look good if you want to deploy your industrial reliable communication in this channel. And this is taken in an office environment with few devices operating. Anyway, if you look if you zoom in time, we see that we have some transmission opportunity. Because if we transmit while the other network is transmitting, we have so-called transmission in a busy channel. We can have packet error and unreliable transmission. Nevertheless, if our system is able to exploit the many blank spaces, well, the chances of having reliable packet transmission are much higher. The problem is how we do that. Okay, we may think, okay, let's switch to the frequency domain. We have a certain spectrum, and this is the what we see, the interference in the frequency domain coming in an office environment, coming from Wi-Fi and Bluetooth. Well, the blue and green, the green lines show where the interference is acting. Well, it's a bit everywhere. Where do we transmit? We can find some channels, but are these channels allocated? Should we allocate these channels in a static manner? Shall we allocate these channels in a dynamic manner? This is expected to change. So how do we track the dynamics of the interference? Here is where cognitive IoT comes and help us. There is a common approach in literature, which is basically comes from observing the radio channel, identifying the interference, and then coming with some ideas for mitigating the interference. In particular, the observation data comes from energy sampling. Your device, IoT device, is sensing the radio channel, is sampling the energy, and or analyzing the errors that are inflicted by the interference on the packet level. Based on this observation, some algorithmic and or more advanced machine learning methods can be used. And interference mitigation is basically a transmission adaptation. You adapt your transmission scheme to survive the interference. There are drawbacks. The energy sampling leads to long idle times of your network. If you want to monitor the interference, your network needs to stand by, and you need to observe the interference, and then you map the interference in time and frequency, and then you adapt your transmission. But the question is, can your network be in standby if you're transmitting data continuously and you want a continuous reliable transmission? That is challenging. Also, complex machine learning methods, which seem to be very interesting in this context, they require expensive hardware usually. For example, deep learning or this kind of approaches, which are very difficult to implement, if not impossible, on low-cost IoT devices with kilobytes of RAM, so to speak. This is where we frame our work. Global aim is improving communication reliability, which can mean a lot of things, and it can be done in many different ways. Okay, one approach is to develop mechanism for making the wireless sensor network self-recoverable. The second approach is the one that we are discussing, is investigate how to achieve wireless coexistence in a lightweight and implementable way, not just theoretically. In our work, we propose the following approach: 3 blocks, as described before, but we use energy sampling in a lightweight manner, and we use some mathematical model aided spectrum features to minimize the effort in sampling, so that the sampling itself can be done without particular effort, even with low cost $40 IoT devices. Interference identification, how do we address this? Well, we somehow touch the edge of machine learning just with supervised learning, but we do it in a scalable fashion. We start with very simple methods, and we scale up the complexity of the method to see how far do we need to go for having a good identification performance. And moreover, we have to do this in real time if we want our system to be adaptable. Interference mitigation. Well, if we are able to classify the interference in a real-time manner and in very accurate manner, we can have a technology-specific medium access optimization. We can understand who is transmitting on which frequency, at which moment, at what time, and we can come out with highly reactive medium access protocols able to survive interference. We have the following contribution for this work. The method is that we deployed is quite accurate. There is 90% of accuracy and covers the identification on the most important and widespread wireless technologies in the IoT context. And it does that by analyzing a single signal burst. So it classifies single signal bursts. It doesn't need much time for sensing the channel. The processing is done locally, it's done on your chip sensor node without particular processing efforts due to good optimization efforts, and it doesn't need to transmit this data for being processed offline somewhere, but it does that locally. It identifies self-interference. Many of these methods are available in literature. They need the network again to be in idle time, so be in off state. Network doesn't need to transmit during the sensing time. Our method is able to identify using energy sampling the transmission of the same network. So your network can keep transmitting while this mechanism is working. On the implementability side, we have smart spectrum sensing, which is non-invasive due to the features that we have discussed, and we implemented this on 50 years old WSN devices, the TELUS-P devices that Mezan mentioned beforehand. This scalable supervised learning, we called it, is indeed implementable itself in these devices. So these devices can process the observational data, come up with a conclusion on the identity of the signal burst with processing delay less than 1 millisecond, making it quite fast and implementable in real-time applications. So what are the next step? Okay, next step that we are planning to pursue is that comprehensive interference-aware medium access. So how do we use this information that we have acquired, that very detailed information about the interference, in the context of improving our transmission reliability in practice? And how can we include this information in network diagnostics? So as said, for example, in automation, you need very high reliability, so you cannot really allow your network going off, the communication being unreliable for seconds, because the packets are transmitted on base of milliseconds, tens of milliseconds. So if we are able to identify the transmission of the interference in this in real-time manner, well, something in the context of real-time recovery, self-recovery of the network can be definitely done. Okay, thanks for your attention.
Okay, time for questions to Simone. Slow crowd this afternoon. Yes, thank you.
Thank you. My question is a curiosity. The technique that you have presented, have you tested or related to the fundamental frequency of each wireless communication? Because I mean, maybe for an higher frequency, you have a less slot time really small for the identification, so for the real-time execution. If you done this type of test or something like that?
We have tested the solution using the 802.15.4, so the ZigBee hardware, and we have tested it on the 2.4 gigahertz band. We have repeated the test for all the common technologies that are transmitting on this band, which are Bluetooth, basically, Wi-Fi, and ZigBee itself, and also Bluetooth low energy. We try to differentiate this. These technologies, they have different emission spectra, so they have different bandwidth basically, and they are also different packet size. So some of this can be really quick, some of this can be can transmit really long packets. And in this paper, the third paper here, we discussed, okay, how is our system able to scale down in both temporal and in frequency. How does the accuracy, how is the accuracy affected in both time and frequency?
Thank you.
You're welcome.
Do you have any other questions? Maybe a very short, maybe very obvious one, but I mean, you have this smart way of adapting. Why would you not just switch to another frequency? What would be the reason to pay for this extra complexity, you could say?
Yeah, this is a good question. The problem is, I can quickly go back to the slide where we show the spectrum. Okay, we had a hypothesis. Okay, how wireless system works in this unlicensed band, this 2.4 gigahertz band. We cannot really go for the left or right, so to speak, because here we can transmit for free. So if we manage to do some sort of transmission adaptation, so we know how the interference look like in frequency. This is a picture taken with the spectrum analyzer. You really don't have that on commercial devices. And okay, so if we are able to understand the frequency configuration of the interference and we to track it in time, then okay, we are able to do this channel selection within the band. The other question is, okay, then why don't you directly switch band? You go to sub-gigahertz or you go higher. Yeah, that will be that is interesting, but still it changes totally changes the configuration of your network. So it is something to be of course investigated, in particular to go down in the sub-gigahertz ISM bands where you still can transmit for free. You have less bandwidth, you have no or less interference because Wi-Fi, Bluetooth, they don't work on that band. Yeah, that is an interesting. But of course, you have the drawback of less bandwidth.
Great, thank you.